So welcome on the second talk on SDP hierarchies by Steurer.
Thank you. So I wanted to finish some of what we discussed yesterday, and to have the time better under control. I made some slides. If it works. What did we look at yesterday? So we had this promise problem in games that had the parameter epsilon, and so you remember you were given a bunch of equations involving two variables, modulo k, and we wanted to find an assignment to the variables that satisfies as many of the constraints as possible. And we were promised that there exists an assignment that satisfies a 1 minus epsilon fraction of the constraints. And the approach for finding such an assignment was to consider a pseudo-distribution that models a probability distribution over these assignments that satisfy a 1 minus epsilon fraction of the constraints. And here just everything that you need to know about the definition of a pseudo-distribution. So it's a function defined, a real-valued function defined on assignments to the variables, and we have this notation corresponding to the expectation of some arbitrary function with respect to the density d, and then we enforce some conditions. That pseudo expectations of squares are non-negative. Pseudo expectation of 1 is equal to 1, and this condition, which corresponds to saying that you satisfy 1 minus epsilon fraction of the constraints. If you would do this for polynomials up to degree d, that would just mean that probability distribution over assignments satisfy 1 minus epsilon fraction of the constraints. And now we relax this and only enforce these consistency conditions up to degree d for some d. And that means that we can also represent this density just by its low degree part without loss of generality, and that allows us to compute these things efficiently. But just, the fact that capital D is low degree is not, can be assumed low degree is not part of the definition of a pseudo distribution. So that's not something that you have to worry about ever. So one property that falls out of this condition is that if you condition the distribution d prime, the distribution d, and get a new pseudo distribution d prime, and sort of in a way such that d prime. So we saw that conditioning certain events preserves the condition that d prime is a pseudo distribution, and this condition here implies that even if you condition on any kind of event, the resulting pseudo distribution d prime will still behave like it satisfies a 1 minus epsilon fraction of the constraints. Actually,
still on average.
Say again?
Still on average.
What do you mean on
not
average?
Not for a fixed int.
Yeah. So here we average over the equations in the instance. Exactly. And this is equal to 1 minus epsilon. Not just wait. Okay, so that's the setup. Now we saw that by conditioning on events carefully, on a few events carefully, we can get into the situation where the variables are uncorrelated on average with each other. So if you pick two indices uniformly at random of variables, then and you look at the mutual information between xi and xj, it's very small, roughly 1 over r, when we allow sort of the degree to drop by r. Okay. And the question was how can we exploit this? And the reason why for unique games you can hope that this sort of has an interesting effect is because if you look at this kind of a condition, that xi is minus xj is equal to c with high probability, with probability close to 1, then this means that either xi or xj are fixed to a particular value, that happens to satisfy, are fixed with probability 1 minus epsilon to a particular value that satisfies the equation, or the distribution of xi and xj has to be very correlated, almost perfectly correlated. And it turns out you have to use the right measures for correlation if you want to you want to deal with this sort of at the right granularity, but that's sort of something that you can do. It's not too hard. Now, now we see that there's some tension between having small global correlation and so this global correlation refers to that we pick two indices at random, but at the same time, if we pick two indices that participate in a constraint, then the correlation is high. So this is the local correlation is high, the global correlation is small, and so we ask, what does it does it say something interesting about the instance if we have this kind of discrepancy, and it turns out to be the case. So what you get directly is a surprising probability distribution over real numbers on the constraint graph, which is the graph formed by connecting indices I and j if the variables xi and xj participate in an equation of the instance. Okay, and what does it mean to have this surprising? So what do I mean by a surprising probability distribution? So it's a probability distribution over Rn. So a real number for every vertex in the graph, and it has the property that if you look at a random edge, then the random variables are very very correlated in this sense. And if you look at two random indices, two random vertices, then the correlation between the random variables xi I and xi j is very small. Okay, so we have a graph that supports such a probability distribution. And the question is, what does it mean about the graph? Yes.
Is this because there's a unique game solution, or? Or this is just a property of your.
Yes. So why is the claim true? That's a question, or
because there's an STP solution.
Yeah, I mean, so it requires a proof. So this claim, I will explain the proof on the next slide. It's a somewhat non-trivial kind of. It's not trivial in the following sense. So here, we talk about a particular kind of correlation, namely the kind of correlation that says that, these variables, they satisfy a linear equation with high probability. And here we talk now about another kind of correlation, that you have two real-valued random variables that are correlated with each other in sort of in the best way that you can hope them to be correlated, right? So this, this ratio, this here can never be larger than this quantity. So this being 1 minus epsilon is sort of as large, almost as large as it can be.
So the low global correlation, you need to do some work to move it from mutual information to this form? Or?
Yes, yeah. So that's the.
And then that's the key solution. You need to do some work to move it from there to this form.
Yes. So the work involved exactly is somehow relating this notion of correlation and this notion of correlation. We somehow, like a priori, these two notions of correlation are a bit, incomparable, and now you want to unify them into one, into this particular notion of correlation. So yeah, what we're doing here is translating between correlations, and so the reason why we can do that is precisely because because we have an STP solution, or because another way of saying it, because the pseudo-distribution satisfies the condition that I stated before. Yes.
In the STP setup, should I think of this zeta I as some kind of Gaussian projection of average of tensor vectors?
Exactly, yes. And but we see that there's actually a somewhat intuitive interpretation of these tensor vectors in terms of pseudo-distribution. And okay, so why is this? So what does this mean? So this, I'm claiming that this means something about the graph. And what it means about the graph is that, first it means that the random walk on the graph mixes very slowly. In the following sense, even if you do this number of random steps in the graph, you see only a very small fraction of the vertices. So the distribution will not be uniform over all vertices, like you would expect after lots of steps. We would expect that the distribution is uniform over all vertices. But this condition implies that even after this number of random steps in the graph, from particular vertex, your distribution is concentrated on roughly an n to the minus beta fraction of the vertices. Okay. So this property about random walks on the graph, and now, question is what's the combinatorial reason why can we sort of derive combinatorial consequence from this slow mixing time? And indeed, that's the case. And what it means is that if you take this much time to mix, then basically the reason has to be there exists a set that is very small, and its expansion is very small. And the reason why that's the case, sort of maybe easiest to see in the contrapositive. Okay? So if this would be not true, so meaning every small set has large expansion, then that gives you a way to just check that actually the random walk mixes quickly. Because in every step, you sort of you see if the expansion would be larger than this number, you see let's say an epsilon over beta fraction of new vertices, and that means that after this number of steps, you sort of see everything.
David, what is beta?
Beta? Yes. So beta is introduced here. So this is
saying gamma.
Yeah. The gamma here is from the global correlation. And so if you choose gamma to be if gamma is if you choose beta so that it satisfies this relation. It's just reparameterizing this a little bit so that we don't have logs, too many logs appearing here. Yes.
So this follows because if you have a short random walk between two pairs, then their correlation must be high.
Yes. So that's a good question. So why does this condition imply that the random walk mixes slowly? And that's exactly what you said. So what you can show is that is the following. If you if psi satisfies these conditions, and now you pick not just one random step but t random steps in the graph, then the correlation between the endpoints of the random walk is at least 1 minus whatever it was before, the correlation it was before, raised to the t. Yes. And so that means that where does now this strange number come from? So that's a number that you need to. So okay, let me back up a little bit. So I want to say that the random walk mixes slowly.
1 minus over.
So you just want to compare this 1 minus epsilon to the t to gamma, right?
Yes.
So gamma
Right. So now I look at what's the correlation that I have left after beta divided by epsilon times log n steps, and then this here, if you choose this number as t, this here will be much larger than n to the minus beta, which means that, or it will be much larger than this number, and that means that that your random walk hasn't mixed, because you know that if you sort of pick two vertices according to the stationary distribution, the correlation is very small. But what we picked here, two vertices according to the random walk and the t-step random walk, and the correlation was very large. Was much larger than in this for the stationary measure, and it means that you have a mix. Okay. Now, what's the proof of the claim? So the details are a little bit a little bit technical, so I'll just give you some high-level idea. So it turns out that like what's useful, so we want to construct now somehow these random variables on the graph. And what turns out to be useful is to consider the following new pseudo-distribution, which is just the product of the tensor product of our given pseudo-distribution. And this is actually a completely valid operation for a pseudo-distribution. So this here will now be a new pseudo-distribution, and instead of being distributed over good solutions, it's distributed over pairs of good solutions. And because it's a product, it's independent two copies. And it still satisfies all the conditions that we want from pseudo-distributions. Now we can define a function on this on this new space, low degree function that satisfies exactly the kind of properties that we want, in the following sense that if this condition is satisfied, if xi and xj are linearly related with property close to 1, then the correlation between fi and fj under the pseudo distribution is close to 1. And similarly, if the variables xi and xj are uncorrelated in the in mutual information sense, then the correlation of fi and fj under the pseudo distribution is very small. Okay, and so if you have such functions fi, then you sort of follow the same reason as Then you can just sample a Gaussian random variable with the same covariance as fi and fj, and because it's a pseudo distribution, like the covariance of this is positive semi-definite, and so you can actually sample such a Gaussian distribution.
That would be the C.
Say again?
That would be the.
Yeah, exactly. The xi would be any random variable that has the same second moments as fi. And then it exists just because we have these square polynomial conditions, or because it's an STP program. But notice that somehow like this, this function here can be a little bit complicated. So it's not the relationship of fi to the vectors. Expressing it in terms of vectors is somewhat surprising. But so how does the function look like here? So it turns out that essentially the following function works. The following functions work. So the function fi, given two assignments x and x prime, will be either equal to minus 1 over k, or equal to 1 minus 1 over k. And like what you look at is whether the values for xi are the same in both x and x prime. Okay, so you check whether x and x prime, whether xi is equal to xi prime. If that's the case, then you output 1 minus 1 over k, otherwise you output just minus 1 over k. And there's a slight catch, and this sort of makes everything a little bit ugly. So this precise choice only works if xi has full entropy in the distribution d prime, which is a little bit cheating because we obtain d prime by conditioning, and that tends to reduce the entropy. So, but it's only cheating in the sense that you have to choose fi more carefully in the general case. But that contains the main idea. So why does this make sense? It's actually like you can really it's sort of if you look at this full entropy case, you can convince yourself that it satisfies these conditions. So so one property that this has is that the expectation. So if you choose x and x prime, the claim is that the expectation of fi is equal to 0 under the pseudo distribution. The reason is that if this has full entropy, then the event xi is equal to xi prime happens with probability 1 over k. So that means that in the expectation, this contributes 1 over k, and this contributes minus 1 over k, so the expectation of fi is 0. And that means that if xi and xj are really you know, if this mutual information is close to 0, which means that xi and xj are close to pairwise independent, then it means that, you know, this this expectation is close to the product of the expectations, you know, expectation of fi times the expectation of fj, and that's 0. Okay, so this is okay. Now, why is this true? And this is true because, you know, if xi is equal, if xi and xj satisfy this linear relation with probably close to 1, then you know, basically if xi and xi prime collide, then also xj and xj prime collide. Okay, so those two events are perfectly correlated, and that means that this inequality is true. Okay, so that's the sketch of the proof of the claim. Now let me give you a high-level view sort of the whole algorithm. So the whole algorithm, so meaning, you know, so you get in a game's instance a set of equations, and you compute the pseudo-distribution. Now, how do you get an assignment? How do you compute an assignment? So here's the overview of the algorithm. So there are 3 steps. I'm showing currently 2 of the steps, and you repeat the steps, you know, as long as possible. So first thing is that, so you look at the connected components of the constraint graph, and if one of these components has large global correlation, measured in terms of just you know, for the component, then you condition on an event in that component and reduce the average entropy of the variables in that component by a significant amount. Now, okay, so if all components have low global correlation, we can look if in any of the components, you know, is it true that most of the variables are almost fixed? Okay? So then we can just read off a good solution for that component, and you know, we choose that assignment, and you know, it will satisfy most of the equations in that component, and so that's good, and we can continue. Now, if all components have low global correlation and the entropies of the variables is large, then what we saw is that it has to be the case that, you know, the random box on this component, it mixes slowly, and that means that we can cut out a set of that component that you know, whose size is n to the beta fraction smaller than the size of the component, and where the expansion is small. Okay, so that's the whole algorithm. Now, what's the analysis? So we can think of this as the recursion depth is maybe not the right word here, but we can associate some depth in this process, and in the sense that, you know, when we cut out a set, you know, think of it as that new set, that small set here will be we think of it as depth being 1 smaller. So the component that we create here, you know, define its depth to be 1 plus the depth of the previous component.
How do you identify the set that you want to cut off?
Okay. So that's, you know, if the random walk mixes slowly, then it also means that you can efficiently find these sets that don't expand. So you just you know, compute the distribution of the random walk after a certain number of steps, and then you know, there has to be sort of one time step where, you know, this very quotient is of the Laplacian is very small, and that means that you have a set that is a small expansion.
Okay.
And yeah, so maybe there's a nice picture that you can draw. If that's this component that you're looking at here. Now you pick some vertex. Now you know that the random walk mixes slowly, so it means that, you know, if you take one step, you maybe distribute it here. Once another step, you distribute it here. You know, even after log n steps, you know, you're still distributed around the very, you know, on a very small part of the component, and so it means that, you know, in one of these intermediate steps, the expansion was very small, and you can compute these intermediate steps.
This first thing, if it has global correlation greater than this, that's where you use this Gaussian, where you're sampling from the Gaussian. Where is it that you're sampling from this?
The sampling. So in some sense, the sampling is really only to prove that the random walk mixes slowly. So you don't have to actually sample in the process. So if both of these steps fail, then you know that the global correlation is small and the local correlation is large, and then there exists this distribution of real numbers, and that certifies that the random walk mixes slowly.
It's just to prove that theorem.
Yes. Okay, and so it means that in the number of times, okay, because whenever we sort of create a new component, its size is into the beta fraction smaller than the previous component. It means that we can, the number of times we can sort of go to smaller components is at most 1 over beta. Okay? So it means that we can sort of arrange the computation into a tree of depth 1 over beta, and it turns out that because we only cut things that have expansion at most root epsilon divided by beta, in each level of the tree, the number of total fraction of edges that we're deleting is at most this much, and that's the number of levels that we have. So this here tells us what's the total fraction of edges that we're removing from the constraint graph. And here, these edges, they correspond to the equations that we want to satisfy. So we are sort of giving up on those equations. And the rest of the equations we are satisfying, most of them we are satisfying in this step. So as long as this number here is smallish, we are in good shape. And so it means that if we choose this number is smallish, if we choose beta to be roughly epsilon to the 1/3, small, larger than that. And that means that, okay, what does it mean? So it means that for this global correlation, that's sort of the bound that we can tolerate. And this bound here, this here was so the bottleneck here is this here has to be comparable to the degree of the pseudo expectation, because if you want correlation to be global correlation to be this small, we have to condition into the we have to be able to condition into the beta times roughly, and so it means that the degree of the pseudo distribution should be at least into the beta. And so that means the total running time of this algorithm is 2 to the n to the epsilon to the 1/3. Exponential in the degree of the pseudo distribution.
So I still don't understand what is the exact claim that you're making about being able to identify these small cuts? So there's something like this, you obviously don't find the exact set of expansion. Right?
Yes.
So what find something else?
Yeah. What you find is so look at these. Okay, so we established that the random walk mixes slowly. Now we have these distributions, and the way these distributions look like is G. So if you start at some vertex I, then the way the distribution looks like after t steps is like this. And now what you get is that this here, you can think of it as that's the collision probability of this distribution. And this is very closely related to basically the size of the support of the distribution. And so it means that
it's a Tigger bound, right?
Yeah.
Okay.
I mean, the question is maybe to what function do you want to apply the Tigger bound to? And what you get from this condition that the random walk doesn't mix quickly is that there exists some t such that these two numbers are at most this here. So this we expect this to decrease. So this here will be at least 1 minus epsilon divided by beta. Okay. Now what does this mean? So now if you rearrange this, you can think of, if you look at the function now, g to the t minus 1 times
Oh, okay, yeah.
So
I guess
this function will be a function where that you can apply the Chiga bound to.
Yeah, okay. So you're not really finding you're just, this is an upper bound of the expansion.
Yes, yes.
But what you're really finding is a small eigenvalue.
No, it's tricky to think about it in terms of
Right.
eigenvalues. Because, I mean, what's really important is that the reason what prevents us from talking about eigenvalues in the way you usually talk about in the context of Chiga's inequality is because we want a small set.
Yeah.
Okay, and the reason why you get a small set in this, if you sort of look at this function, is because this function will have a large collision probability, relatively large collision probability. So it means that this function, as a set, corresponds to a small set because it has large collision. But yeah, maybe this picture here is this is really like the sets where the distribution is concentrated after a different number of steps in the random walk, and all these sets are small. That's one promise, and there are many steps that you can do, and that means that one step has to be has to have very small expansion.
I see.
If you use fewer levels of the thing, this n to the -2 beta is hopeless?
Yes, okay, so that's exactly what I wanted to discuss next. So what's the... so what's... Maybe the more general question is, how could we refute... I mean, why does this not... why could you not do something similar and refute the Unigames conjecture? And so as you said, like why do we need this very small global correlation? Or do we actually need this? And in some sense, we indeed need very, very low global correlation. So there are examples that show that you can have very low global correlation, but still, but no good partitioning exists at all. Okay, so it's not just about the algorithm that you use to find the partitioning, but the examples that show that where you can have very low global correlation and it's just not possible to partition the graph. Okay. And these are somewhat intricate constructions based on locally testable codes. Somewhat surprising connection. And these examples are actually not just ruling out this particular. They're not just saying something about this particular approach. So it turns out that basically the same examples, they also show that if you only look at monomial moments in the pseudo-distribution, then you have to, then you need to invest super constant degree, which means that you cannot hope for a polynomial time algorithm. And here, this loop here comes with some restriction. So what the code Poppert and Sackett show is that there exists a pseudo-distribution who, that in terms of the monomial moments is very close to satisfying all the constraints that you want to satisfy, that you want the pseudo-distribution to satisfy. And so it means that, if the way you look at these monomial moments is, unless you're really exploiting that things look exactly like they're supposed to look like, which is sort of unintuitive in the context of approximation algorithms, then, what their construction shows is that you need to have a super constant degree.
But other moments are just linear combinations of monomials.
Yes, exactly. But if you do linear combinations, then things that look okay in terms of monomial moments, they might look very far off in terms of after you take the linear combination, because the linear combination it might accumulate errors. So basically, there are these monomial moments. They are okay up to some errors, but they still satisfy that squares are non-negative, for example. So it's really like
Squares of monomials are not negative.
no, squares of arbitrary polynomials, they are non-negative. But now if you sort of look at, you want to satisfy the constraints, and that's sort of where there are some, where only, where things that don't hold exactly, but only up to some level. And so that's sort of what motivates, okay, and now, okay, so you might think that, okay, maybe this means that, so maybe it's not a problem with these monomial moments, maybe it's just a problem with the whole approach. But it turns out that if you look at the pseudo-distribution, if you look at these things in the right, if you look at these moments in the right basis, as you said, it's just a basis change if you go to other moments. But it turns out if you look at it in the right basis, then there's a very easy argument, a very robust argument that shows that that these instances, these examples are not a problem, and the right basis turns out to be the eigenbasis of an appropriate operator. And this is what motivated this way of thinking about these SCP solutions in a basis-independent way, and which is what we did with, which is what the goal of these pseudo-distributions, the pseudo-distribution viewpoint for these things. Okay.
Is it obvious that the squares are non-negative in the Kurt-Popper-Sake? I mean, they give SDP vectors.
Yes.
But, for example, when you compute the expectation of a polynomial and you square
Yes.
it, you will sort of want to replace these moments consistently, or when you so when you think of when you get a term S delta t, you would want to think of the product of S and t.
Right. So I guess
products, but there you will get errors. So once you try to substitute the inner products of the SDP vectors into this polynomial, you will have to substitute each term with an error.
yes. Okay. So maybe one way to say that is that like the commutativity properties are not satisfied as you would expect. Then
But then that would break the positivity of squares.
it depends what you mean by squares.
But your next result wipes these things out anyway, right?
So again, yes. So this is not a very this is more a question of taste. But it means that it really means that if you sort of look at monomial moments, then you have to be very careful with if you want to avoid this this obstacle. But and the fact that sort of it becomes very easy in the right basis is maybe also motivation to look at things in basis independent way. Okay. So now I wanted to okay, so let's do some time. So I wanted to talk a little bit about more recent developments in the context of some squares, also at the higher levels, so not as technical as what we did just now. And so it's the following problem that I wanted to talk about. So it's you want to find the sparse vectors in a subspace. Okay, so what the setup is you have a d-dimensional subspace U of Rn, and you're given it in some by some basis vectors, an arbitrary basis, and the promise is that the subspace contains a very sparse vector, and your goal is to find such a sparse vector in the subspace. It is actually quite closely related to the unique games conjecture and the problem that we talked about before. So it turns out that this problem is at least as hard as a problem called small set expansion. And that's and the correspondence is most clearly in the case when the sparsity of the vector that you're talking about is comparable to the number of coordinates of the vector. And basically, small set expansion is a problem that you need to solve if you want to refute the unique games conjecture. And so polynomial time algorithm for small set expansion would be, or even a quasi-polynomial time algorithm would be a major step towards refuting the unique games conjecture. And so that's the was our motivation for looking at this problem. But it turns out that actually the average case version has also been studied of this problem, and and here it turns out that we can say something new. And so the average case version of this problem is that you generate the subspace in the following way: you pick d-1 random vectors, say random Gaussian vectors, and one which can actually be an arbitrary case sparse vector, and you look at the subspace spanned by all of these vectors. and you're given it some arbitrary basis, maybe a random basis. And now you want to find the sparse vector. So that in some sense you make it, you plant one sparse vectors among p-1 random vectors. In this problem, one way to think about it is some kind of benchmark problem for various unsupervised learning tasks. So, for example, one previous work, this problem was studied by Spielman, Wang, and Wright, and their motivation was to solve a problem called dictionary learning, which is a very basic unsupervised learning problem. And what they but it turns out that the problems that have been suggested by Spielman, Wang, and Wright, and slightly different from by them and afterwards, they have a limitation. Namely, they only work for very sparse vectors. Okay, so the sparsity of the vector has to be small compared, if the dimension of the space is largish. And which is actually sort of not something that we wanted in the context of small cell expansion, because here we really wanted vectors that are sparse just compared to the number of coordinates. And the algorithm that they're proposing is actually very simple, very nice. You look at the subspace and you find in the subspace a vector that maximizes this ratio. So it has the largest infinity norm compared to the L1 norm. And this is something that you can do exactly using linear programming. The reason is that you guess which of the n coordinates of this vector is the maximum, and then you minimize the L1 norm over the subspace with respect to the constraint that you're large in the vector is large in that particular coordinate. So there's a somewhat non-trivial this kind of very popular L1 minimization thing going on over some affine subspace, and the affine subspace that you look at is determined by your guess for the infinity norm. And but it turns out that if you use degree 4 pseudo-distributions, then you can solve this problem for a larger range of parameters. In particular, you can solve it in the full sparsity range up to where the sparsity is up to a constant fraction of the coordinates, as long as the dimension of the subspace is not too large. Okay, but if you choose D to be root n, then here you need this thing has to be still significantly much sparser than the constant times n. Okay, and so I don't have. So now I'm switching to the board.
So if you don't have the promise problem, the decision problem, it's hard.
If you mean NP-hard or?
Yeah, decide if, don't find vector, just decide if the subspace has something.
Yes, this should be hard in the usual sense. I mean, I'm not sure if. So even approximating this in a general, even actually the kind of approximation that we wanted for small expansion, you know that you need at least quasi-polynomial time to do that. So in some sense, this problem, even with the promise, it's it probably doesn't have a small polynomial time algorithm, but for the Game conjecture, even a quasi-polynomial time algorithm would be very would refute conjecture. So
and if you relax the sparsity, so you just want a vector that is very unbalanced.
Yes, that's not implicitly always what we are doing.
Oh, I see.
And it's still hard in this sense, and also in quasi-polynomial sense, even if you relax these conditions. So how would you how can we use pseudo-distributions to solve this problem? So in some sense, the right thing that you would want to do is you would want to find a vector in the subspace that maximizes the.
Can you try to use a bit of them?
Yes, yes.
And maybe
So
less
larger
light.
font.
Yeah.
Say again?
A larger font.
Yes, larger font. So the right optimization problem that you would want to solve, in some sense, would be to maximize the 2 norm compared to the 1 norm. So we want to find a vector that has large 2 norm compared to its 1 norm. You know, and instead of just finding a vector that has large infinity norm compared to its norm, because those basically, if this condition is violated, then if you do this, then there will be you will get a vector that's completely unrelated to the sparse vector that you wanted to find. But if you have this condition, then that would succeed in essentially in the full range of parameters. And so what would be a natural thing to do for this? So you would want a pseudo-distribution, and it would now be a function on the unit ball of the subspace U. Real valued function of the unit on the unit ball of the subspace U. Real valued function. Unit ball. And so it means that now we have to think about integrals. But actually we don't have to think about integrals because we will because these things are all, you will always represent these things as polynomials, and then integrating polynomials over the spheres. I think no one how to do that. And and then you have you would have the usual conditions, that squares should be non-negative. And now you somehow want to say that that the 1 norm is small, and here's some point where you run into trouble, because if you look at the 1 norm, actually maybe let me restate this a bit. So what would you expect the 1 norm to be of a k-sparse vector? As k-sparse unit vector, so we expect k coordinates of value roughly 1 over k. So you would expect this 1 norm to be k times 1 over root k. You would expect it to be root k. Okay, so now you would want to add the equation that the 1 norm should be root k. But now the issue is that the 1 norm here is not a polynomial. In the sense of functions on this ball, and this makes things very complicated to reason about. Now one way to resolve this, which is actually which has been suggested in a paper by on Sparse, so using semidefinite programming for Sparse principle. Sparse principal component analysis is that you instead of so let's look at the square of the 1 norm. Okay, so it will still not be a polynomial, but let's do it anyway. So this this would be the square of the 1 norm would look like this. And now, what people have been suggesting is that maybe we relax the constraint that the 1 norm is small, and instead just enforce that. So we want to minimize. I'm sorry. So you instead have the constraint that. instead of saying this here is less than k now because we squared the one norm, instead of saying that this is less than k, you say that this here is less than k. So you remove the you put the absolute value signs outside, which makes things only smaller. So this is still satisfied by sparse vectors. And now we can solve this efficiently, because it's a convex constraint on these numbers, and efficiently checkable convex constraint on these pseudo distributions. Yeah, unfortunately, for this problem it fails. Also, fails quite dramatically, and the reason is somewhat nice reason. You can choose D to be an actual distribution and make this fail. Okay, and you can just choose D to be the uniform distribution over the sphere and over the probably should have said here that this is the L2 wall. So you could choose here this D to be the uniform distribution over the L2 wall of the subspace. So now this would actually be an actual distribution, but if you compute that if U was a random subspace, then so I guess here what I mean uniform, yeah. Here what I mean uniform, even uniform just over these D minus 1 vectors. So then it turns out that in this case these expectations will be very small. I think okay, I'm not exactly sure if it's there's a root D or just D, but in any case, if you now look at the sum, this would always be the sum here would always be even if your distribution was just this uniform distribution over the wall, it would be less than n over let's say n over D, and it means that unless k is smaller than n over D, this distribution looks like it's a distribution over sparse vectors, okay, with respect to this constraint. And so that's bad. So this is basically sort of as much of a problem as here. And now what you can do instead, which turns out to work better, is use an appropriate degree 4 polynomial, and the right degree 4 polynomial, if you want to enforce sparsity, would be that you add the constraint that x. The fornorm of x, is k times 1 over root k to the 4, which is k squared, which is 1 over k. So you add the constraint that the fornorm of x to the 4, which is a degree 4 polynomial, is at least 1 over k. Okay, and so this is satisfied by k-sparse vectors, and so I guess this here was just a computation. And it turns out that so if you enforce the condition x this is equal to 1 over k, then it turns out that the pseudo distribution will be concentrated on the vector v. Okay, and so it means that you can basically read off the vector v just from the degree 2 moments. But you need to enforce this condition about the degree 4 moments. And the proof that that this condition is recovers the sparse vector is I guess I don't have to write something. It's in a sense very natural. So what you do is you just prove that So if you solve this, if you would solve this problem, exactly, without pseudo-distributions, just if you just prove that the vector that is larger, that has this larger forenorm in the subspace, and the unit vector that has this larger forenorm in the subspace, you give a proof that this has to be close to the sparse vector V, and it turns out that you can prove it in a way that that is very explicit. Okay? Explicit in the sense that the proof uses only the squares are non-negative, and the kind of inequalities that are used in the proof only use that squares are non-negative. And now you notice that that these properties are also satisfied by pseudo-distributions, and that means that the pseudo-distributions capture this proof, and therefore the pseudo-distribution has to be concentrated on around the vector V. So that's what I want to say about this problem. Thanks a lot.
Questions?
Thank you very much. Start again now.